Hello, is it okay?
Yeah.
Fine. Then switch it off now.
I'm also joined in. Oh, yeah, Hi, Raghu.
Hello,
Hey, hi.
I joined. I thought of coming there, but anyway, evening we have to go somewhere else, so it will be inconvenient. So I thought I will attend through Zoom.
No problem. Krishna
Okay.
is also joined.
I
Krishna.
see. Okay, good.
Yeah, I'm also there, Ambar Chatterjee.
Satya is also good. Yeah, Satya also. He said depending on his connectivity in the village.
Hi. Hi, hi.
Hello, I joined on Zoom. This is Satya.
Good.
Thank you, sir.
Hi, Unni.
Hi. I'm here.
I think we will. Is it nearing 4? Yeah. Okay. Yeah, perfectly fine. Yes. You wanted on dot because he has the CS. Yeah. Hello, good afternoon, everybody. And it's a pleasure to welcome here Professor Datar to give us a talk on journey in nuclear physics and intersection with high energy physics. Professor Datar is well known to this audience, so not require any much of an introduction as such, but I will just say he had a very long 40 years of excellent service to our nation in BRC as a head of NDP there, Nuclear Department Physics. I request Professor Datar to please.
So 5 years. Yeah.
And 5 years in CAFR being, I know, head for international things. So, without further ado,
So we should take this thing on. Yeah. Hello. Yeah. That's okay. Okay, so let me thank the asset organizers, including the new person who will conduct this in the future, Parag. And also I thank Satya for helping organize this. So this is the brief outline of my talk today. There's a little bit of history, some of the early years in Van de Graaff lab in nuclear physics division in BRC, then excursion in atomic physics. And this was, of course, due to Professor CVK Baba. Then
Hey, just a sec. We can't see the screen. We can't see the screen.
You can't see the screen?
Yeah.
Screen.
It should be shared on Zoom.
Huh?
It's not shared on Zoom.
I think it is shared.
It is shared.
I can see. I can see. Rao here. I can see.
Okay.
Can most people see? Can Naveen, for instance, see?
I can also see. This is Satya.
Okay. So
Amber here. I'm
maybe
also
there's
able
a
to
problem
see.
on their end somewhere. Okay.
I have no problem.
Yeah. Okay. So then I will come to experiments done with our sort of bread and butter for many, many years, the 14 MV tandem at TIFR, and also the later part where the LINAC was added, superconducting LINAC. And then say something about what is our future in terms of an underground lab, because we have been unsuccessful in getting the INO lab working in Theni. We didn't even get started, actually. So I'll say a few things about that, and then a future outlook, just a slide on that. Okay, so here I go. So let me give just one slide of my background. I did my school and college in Bangalore. I chose NSTS. In those days, there used to be something called the National Science Talent Scholarship. I got impressed by reading books about Madame Curie and Fermi and so on, Feynman. And so I did get admission. And in fact, I had paid the fees also for electrical engineering at IIT Bombay, but I dropped out of, I mean, I didn't even join. So I chose to do a BSc honors in Bangalore. Then I joined IIT again, second time, for a MSc physics course, but I had given an interview, and so I left that as well and joined the BRC training school. Now that was when you look back, it was a slightly risky decision, because if you don't get somewhere in the top 5 or something, then there could be a problem. You have to join a group which you may not like, and in fact there were cases of that sort. But fortunately, I got into CVK Baba's group, and that was a great thing. I think I consider myself fortunate to have done so. So my first job CVK assigned to me was to make a plus minus 12 volt DC power supply. So that was with Vase and Bhalerao in those days. So we built it. First time it didn't work, but there was some dry solder. I had never even held a soldering iron before this. And it was the first time I was learning to use a soldering iron, to use a multimeter. In many of these colleges, I think these facilities are absolutely minimal. There are just some experiments which you have to do and you have to produce a result. So the experimental capabilities of a BSc guy are very poor. You're not allowed to, just hang around there and try something. Maybe something will go bad, but that's okay. So then I was asked to, along with Amber will remember that we were asked to go to the RF ion source lab and actually clean the bottle, the quartz bottle, with hydrofluoric acid. We were told it's very dangerous, be very careful in handling it and so on. We managed to do some things there, and then this ion source was tested in a bench for testing that, and then was put up in the Van de Graaff accelerator. So this, of course, we are told to do by the then head, Dr. M.K. Mehta. Within a month, fortunately, I also was able to participate in an experiment at Van de Graaff, which was a gamma ray spectroscopy experiment, where the late Dr. Bharati, he was involved in that. That was actually part of his PhD thesis, which was somewhat delayed. It was from the 6th batch, but somehow it happened quite late. And so I was involved in that experiment. I got to learn many things for the first time, including the night shift. I mean, what is a night shift? So I got an experience of that for the first time. Oops, we have to use this. Okay, so let me go to some of the early years, and before doing that, let me show you some pictures. So the Van de Graaff, this is the Van de Graaff control room on the left side. So it shows the inauguration which took place in '62, where Bhabha, he's being explained, the controls and so on of the Van de Graaff accelerator by Raja Ramanna. And then there is Divetya on the left of Bhabha, who was the then head of the nuclear physics division. He later went on to become the first director of the variable energy cyclotron at Kolkata. And he was actually, he did, I think, a postdoc or something like that in Wisconsin with Herb, who developed the Pelletron accelerator. So he had the first real experience. Pardon? Sorry, I couldn't. Yeah. Many of these people. That's right. So anyway, then there's the Van de Graaff, which was the workhorse in those days in BRC. Then that was later upgraded to a 7 million volt folded tandem accelerator. So inside the accelerator, they put a magnet, and so the negative ions were injected up and then stripped and then sent down. And this has been working reasonably well, I would say. I mean, it's not that as reliable as the Van de Graaff, but nevertheless, lots of experiments have got done. And this was actually spearheaded by Dr. Pitambar Singh. Just two other facilities which we have used, or I was involved in the usage of that, is the Apsara swimming pool reactor. By the way, this is a very nice thing to see. Now, of course, I think it's closed down. There is the newer version of that elsewhere, not in the old place. And you see this beautiful Cherenkov light coming from the betas which are stopping in the water. And so we were shown that when we were in the training school, but then we actually did an experiment there, which was the first version of the axion search experiment. And then there is this 6-gap orange spectrometer, which was built by the group here at TIFR, CVK, Baba, Agarwal, and so on. And this was an electron spectrometer, mainly to measure conversion electrons. And that was a tool that was not there in many places. So it was, I think, built early on in the Niels Bohr Institute, and a something similar was done in Van de Graaff in BRC. So, okay. So the kinds of experiments that were done was, for instance, this in-beam gamma ray spectroscopy, the experiment that Bharti was involved in for his thesis work. So it showed that there is shape coexistence in 72 krypton. These are, of course, low spin states that were populated through the PN reaction, PN gamma. Then there was an interesting piece of work that had happened before I joined, and that was this 72 germanium PP prime conversion electrons. So the conversion electrons were detected in this spectrometer, electron spectrometer, the orange spectrometer, and they found interesting structures in the excitation function in this particular channel. And there's no explanation for this. So CVK came up with this idea that maybe this is due to states in the second well. So as if you plot the potential energy of a nucleus versus deformation, then there is the ground state, which is the lowest energy state, which could be zero deformation or very little deformation, but there could be some other state with a much higher deformation. And this would be at a higher excitation. The bottom of that well would be much higher, but then the number of states associated with that deformation would be much smaller in number. And if you populate some of these states, then they would mix with the normal deformed states or zero deformed states. And therefore, you would get these broad structures in this excitation function. So the idea was to look for delayed gamma rays. So we looked for it, of course, didn't find it. So we could only have a symposium paper, but it was an interesting experience. This was also the first symposium that I attended, where I made the presentation, and I remember Raja Ramanna coming up and saying, "Have you made a good presentation?" I mean, irrespective of whether the presentation was good or not, it felt good to have Ramanna patting your back. So anyway, then there is this experiment, which was an offline experiment, non-accelerator experiment, which was a suggestion due to Lawson in 74, and which Professor Bhattacharya picked up. And he said, no, we must do this experiment, because this is quite a unique case, and I will have a slide on that, which addresses the question of the mean field radius parameter for the protons and neutrons. Okay, is there a difference between the two? And by looking at the beta decay of thallium-209. This is absolutely unique, because there's no other parallel case that I have been able to find. Okay, then we looked, this was towards the end of the life of the 5.5 billion volt Van de Graaff, which is, of course, a single-ended machine. So we searched for this long-range van der Waals type of interaction, which nucleons could have with nuclei. And so we looked for it in P-led scattering. And this is not the last, this is the second last experiment. The last one was done by Ishwaran's group later on. Okay, then we also, again, this is an offline experiment. We searched for the polyneutron. Can there be a nucleus which consists of just neutrons and nothing else, 6 to 8? Because there is an indication of that in an experiment reported in Phys Letters by Turkevich and so on. In spallation reactions, they found evidence for this. And so we decided that if it is, I mean, the spallation reactions are not accessible to us. There is no accelerator of that type. But why don't we look for it in fission of U-236? That certainly is neutron rich, and it produces, of course, very neutron rich fission fragments. So there is a possibility that these things, if they exist, they might be produced in the fission. And so we irradiated lead-208, and that would have produced something like lead-211, lead-212. So see, we looked for the alpha activities from that, and that's a very low background experiment, because we're looking for specific alphas. So again, this was a negative result, because we didn't find any evidence for these kind of polyneutron structures. There is still some interest, apparently, that there is a claim, I think, in Ganil or something, to have found 4 neutron nucleus, but I think there is no substantiating evidence from other groups. We attempted to also measure conversion electron spectroscopy of neutron-rich fragments in the spontaneous fission of californium-252, which was a source bought for some other purpose in TIFR. CVK had got this to make some magnetic moment measurements, but he was spied, or what do they say? There's another group in Israel that actually did the experiment before they could carry out this. So then he said, is there any other use of this? And so he thought that electron spectroscopy might be a thing. But somehow, again, this experiment failed We didn't quite understand why. We worked on it for about a year. We did all kinds of things using thin plastic scintillators to measure the fission fragments in coincidence with the conversion electrons. We put a metallic evaporation on the plastic foil because we said maybe it's getting charged and that's why the spectra are getting distorted due to electrostatic fields. But we never could figure out why we didn't see any conversion electron spectrum. Anyway, so there are, experimenters usually have such experiences. You fail in some things and you don't sometimes understand. Sometimes you do understand why you failed. This was a nice experiment that we carried out. This was following a visit by Nimai Mukhopadhyay, and he had a very nicely titled paper in physics letters at that time, Axions, to be or not to be. Okay, a quote from Shakespeare. So he was absolutely, he said, you have to do this experiment, CVK, there's nothing, I mean, you have to do it. So anyway, we carried out this experiment initially at Apsara, where we used sodium iodide detectors. And then later we went to Tarapur using germanium detectors, which have a very much sharper energy response. And of course, the background was very high, but that turned out to be actually a blessing in disguise because it provided for internal calibration due to the cobalt-60 activity. Cobalt-60, incidentally, has a cascade of 1.17, 1.33 MeV gamma rays. And so when you put two germanium detectors at a distance such that you don't see scattering, you still see the sum peak. And so that's an internal calibration. So that showed that the detector is working or the setup is working properly. Of course, again, we didn't find evidence. So that together with another experiment using radioactive source, it actually ruled out the so-called standard axion. Again, there will be a slide on that. We looked for electric charge non-conservation beta decay following, the kind of advice of Goldhaber and Feinberg, who said that no conservation law or symmetry is absolute in nature. It has to be tested by experiment. It is only good to the extent that experiment supports it. And so in that scenario, there were experiments already which looked at possible charge non-conservation. In fact, the Goldhaber himself did one such experiment. And we improved on that by about a factor of 40. We didn't find, of course, electric charge non-conservation, and we set a bound. So we have many things like that where you set bounds on various parameters. And these are all mostly non-accelerator kind of experiments. Although, as I said, the Van der Waal was an accelerator-based experiment. Then we searched for the 17 keV neutrino. Again, I have a slide on that. I'll come to that. Then we searched for high-energy Bremsstrahlung gamma rays. Somebody in Japan claimed, I think it was not Koshiba, Kasagi, I think it was. He claimed that he has seen high-energy gamma rays right up to 100 MeV in the fission of californium-252. Now, the total Q value is of the order of 200 MeV. So if 100 MeV comes out in the gamma ray, what is left for the fission fragments? I mean, they have to repel each other, right? And that the Coulomb energy itself is of the order of 200 MeV, a little less than that, 180 MeV. So that means they have to be highly deformed, highly deformed. So it looked odd, but in any case, we did this experiment here with the high energy gamma ray detectors that were there and put a bound on that. Didn't see it. But later, a group in VCC claimed to have seen it. And then I think 10 years later, they repeated the experiment in Jaduguda mine, didn't find it. As we had told them that, please look for this kind of background, prompt versus piling up with cosmic rays. But they didn't pay attention to that in the symposium. Many of these things are presented, but they got a physics letters out of it. And they got other physics letters from the Jaduguda experiment. So anyway, that's to do with the Bremsstrahlung. Okay, so now coming to this difference in the mean field radii, I already mentioned it. Now, normally the electric charge distribution is measured very precisely by electron scattering. That's a very nice probe of, because it interacts only through the electromagnetic interaction. Of course, the weak interaction, but at that's much weaker. So you actually are dealing only with the electromagnetic interaction. And then you can get the matter distribution, that means the neutron plus proton combined distribution, by doing hadron scattering, by doing proton-neutron scattering. But also, if you are sitting on the delta resonance, you can also do experiments with secondary beams of pi plus and pi minus. So the pi plus probes the skin of protons, pi minus probes the neutron skin, okay? Because that's how you can see that from Clebsch-Gordon coefficient, the geometric point of view. And then the kaon is, of course, a much deeper penetrating particle, so you can measure in a better way. But these are secondary beam experiments, so they are relatively tougher to do. But this is generally the scenario. Now, in one specific case, before I go to that, electron scattering, for instance, this was, I think, even in about the early 2000s, that there was this experiment on lead-206 and thallium-205. So there's just one proton separating the two. Lead-206 has one proton more than thallium-205. And very careful experimentation gave the density distribution of the last proton in lead-206 by taking the difference spectrum. And it's a beautiful experiment, absolutely. This is done by the Saclay group in France. So this was the background. As I said, Lawson pointed this thing out in 74 itself. Of course, we did the experiment which got reported in 80. And this was at the instance of Professor Bhattacharya, who saw this. It was actually Lawson's proposal was part of some, I think, summer school or something. I think it didn't even get published. He didn't even publish it in a journal. But it was a very interesting thing. And it turns out that, this, as I said, this is a unique thing. So a 3s half proton in thallium-209 decays to a neutron state, which is a 4s half. Now, the matrix element involves a radial matrix element. Now, you can see if the radius parameters are the same, due to orthogonality. Pardon? The beta decay energy is, I think, of the order of 1 minute. No. I just gave a background that electron scattering is usually done for charge distribution, but we looked at the beta decay. There, in the electron scattering, there's between about 500 MeV to 1 GeV. Okay? Because the probe has to have a de Broglie wavelength, which is less than the size of the, yeah. So you have to have enough resolution. So typically, if you take a Fermi or so as the resolution that you want, then that's the kind of energies that you require. Okay, so this would be forbidden if the two radius parameters are identical. Okay, because then the overlap of the wave function, this 3s half, 4s half, is 0 if the radius parameters are the same. And they would not be 0 if the radius parameters are different. And also, there is a small contribution due to two-particle two-hole admixtures in lead-209 that contribute to this small matrix element, finite matrix element. And so this calculation was actually what do you call this? What should I say? This was done by Professor Varke. He set up the formulation, and then I just computed it. I mean, I didn't do anything else but computing it. And so given that this two-particle two-hole matrix element is in control, we could infer that this overlap, radial overlap, is between these two limits, and that in fact gives the radius parameter difference as less than 2%. Okay, this is I think quite a unique case where you can measure these things to this kind of accuracy. In principle, of course, so we did this experiment with thin plastic for the betas, and for the gammas we use a larger plastic, 2-inch by 2-inch plastic scintillator. So it was plastic coincidence, but this could now be in principle improved by using a better detector for the electron. Even a delta E phosphate detector and a lanthanum bromide for the gamma ray, because then that you can get the photo peak. In that, what we did is we took the whole set of Compton region, spanning a large energy region in order to get statistics. So this is the time spectrum, and then you can fit it, and you can say that this branch is less than so and so, and that's how we put this bound. We searched for this van der Waal interaction in proton plus lead scattering. The background to this was, of course, that there is Savada pointed out by analyzing pi data in the final state that there could be a van der Waal force between hadrons. And roughly at a similar time, there is this experiment which measured the electric dipole polarizability of the deuteron by scattering a deuteron on lead. So in addition to the Coulomb potential between just the charge of the deuteron and this, you also have an additional perturbation because of the polarizability of the deuteron. The deuteron is a pretty loosely bound object, so you can polarize it, and then that gives a 1 by R4 potential. Okay, so that's an additional perturbation. And they actually look for the deviation from Coulomb scattering by putting detectors at forward angles and backward angles. So the forward angle senses the Coulomb interaction, the backward angle senses any deviation from the Coulomb scattering. And in case the beam moves a little bit, because it goes like 1 by sine to the 4 theta, right? The cross section, the Rutherford cross section goes down, and it can change quite a bit if you change the angle. So you have to stabilize the beam on the target, and that we did by this pair of. Why is this not coming on? Oh, sorry, this one. By this pair of magnetic steerers, X and Y magnetic steerers, and X and Y slits. So if it moves towards one side, let's say, then you send a control signal from there back, feedback to the appropriate magnet, magnetic steerer, and then you can shift it back. So this way we could control it to less than 0.5%. Actually, it was like more like 0.2%, because you can look at the singles count rates as well in each of the detectors. And whatever residual shift there is, that is taken care of by the fact that there are two detectors. You can take a geometric mean of them, and that takes, so the contributions only come to a higher order if there is any small shift. And so we did this experiment, and then you basically look for a deviation from Coulomb scattering at larger beam energies, where it penetrates a little more, it comes closer to the nucleus, and then we could put bounds on that. So this is the paper that reports this. And we could put bounds. Of course, we have a series of bounds depending on the N. You can put various bounds, and we didn't see any effect. So again, we ruled out Mr. Savada's analysis. Okay. Then we looked, as I said, for the light mass axion, the so-called standard axion. The axion is, of course, a consequence of strong CP. One of the solutions to solve this so-called strong CP violation in QCD. And that was, there are two papers just back to back, one by Stephen Weinberg and the other by Frank Wilczek. And this was taken up, as I said, by Nimoy Mukhopadhyay in 81. He wrote this paper, and he convinced us that we should do this experiment. So we did this experiment in Tarapur. So you can see the spectrum. The sum energy spectrum doesn't have any peak corresponding to the binding energy. So what happens is you're looking for a signal where the axion comes out, because it's supposed to be semi-weakly interacting with matter. So it comes out and then decays into 2 photons. So if it's the standard axion, this is the signal that you should look for. And we looked at it in those days, there were no high purity germanium detectors. They were just jelly detectors. So you have a P type of germanium, then you diffuse lithium, and then you get the jelly detector. And so these two of them, which were kindly lent by another member, the group leader of another group in Van de Graaff. And so he was a little anxious that, these detectors were hard to obtain, because foreign exchange was not very much available in those days. So he said, please take care, this detector, if it goes bad, we can't do experiments in Van de Graaff and so on. So anyway, we took care, we transported it to Tarapur and then back. And anyway, you see the sum signal, as I said, due to the cobalt activity all over the floor. So in fact, we were operating in a very in a strong radiation environment, and we could only work there for 2 hours in a day. And then we had enough dose that we had to get out. So there would be someone, if we didn't get out, somebody would come and say, come on, now please move out. And the apparatus that we built to record this data was also interesting. There was an old printer lying around in Agarwal's lab. So we modified it such as to we borrowed, by the way, it was all borrowed setup. We borrowed 2 ADCs from Kataria in BRC. We had just procured very fancy ADCs for those times, sort of so-called successive approximation ADCs, very fast. And then they had an output, and then that had to be converted to a BCD output. And then it was given to the printer. So some interface had to be made. And so basically, when there is an interesting event, as decided by the coincidence in energy, some gates, then it would just print out. So in a day, we would have about this length of output. And then I would sit in the guest house and add up. And we had calibrated such that it was half a keV per channel. Okay, so you just add up. So 2.5 would come at 5,000 channels or something like that. And that was it. Work done for the day. And then you wait for the next day data to come out. Anyway, so we put a bound on that. And as I said, together with the cesium-137 search, we could rule out the so-called standard axion. Of course, now this is advanced to non-standard axions and very light axions and so on. It's still not a completely closed topic even to this day. Okay. The next one is the search for 17 keV neutrino. So I don't remember the date, but a little before this, I think in maybe 84 or 83 or something, there was a paper by Simpson in PRL which said that he has seen evidence for a kink in the beta spectrum when tritium is implanted into a silicon detector. So the endpoint in silicon is about 18.6. So for 17 keV, he has to measure the spectrum near 1.6 keV. So already that raises a doubt that at such low energies, can this detector do it reliably? In any case, he claimed a 3% mixing of the 17 keV neutrino. So since we had a reactor and we had radiochemists, we quickly got into that, and we had also completed this search for electric charge non-conserving beta decays. So we had two silly detectors of large area. So we employed one of them, and these were, by the way, made in TIFR. This was made by the detector group led by S.K. Mitra, so the Vaidya, Medhi, and so on. And so we used one of those detectors to set up things very quickly. We got a small chamber made, cryogenics to cool this fellow, and so on. A cold finger, and we could measure the spectrum and then put a bound, which is about 5 times lower than the claimed mixing. And this is the only paper I think I have in Nature. Not I think, this is the only paper I have in Nature. So pretty proud of it, because we got this experiment done pretty quickly. But that was because we already had something which we could use. Okay. An excursion in atomic physics. Let me see how I'm already getting a little late. 12 slides only. Okay. So, pardon? Yeah, that was part of Bhuyan's thesis. Correct. So I should not say it, but the thesis was actually written by somebody else. You know, CVK. Okay. So anyway, again, this was an idea of CVK that he read in some article in the library, saying that, there is one transition in lithium which is supposed to be from a negative ion on lithium. It is suspected that this may be because it doesn't correspond to any of the transitions in atomic or ionic lithium. He said maybe this is in lithium minus. So he got this idea that, oh, this is then easy to test. You can actually make this ion pass in an electric field, electric dipole field. And if it is lithium minus, it will go one way. If it is lithium plus, it will go the other way. And if it stays put, it's lithium zero, neutral lithium. So we did this experiment, and this was done actually in the mezzanine floor, where there was a small 400 kV machine operated by R.P. Sharma, Prasad, and let me see who else, Kurup. So these 3 people were operating that machine. So we could quickly do this experiment. Of course, we needed the help of spectroscopy division in BRC. They provided us with a very compact spectroscope, and which we put in 90 degrees to what is normally used. And so the slit became this way instead of vertical. And therefore, we could look at the whole the excitation or the de-excitation of the beam. And this is the apparatus. So you have, oh, sorry. You have the beam coming in here. It entered a foil. Yeah. Yeah.
Alphabetic order is to be followed, right, for the papers?
Actually, in this one, maybe we have followed that, but I think in nuclear physics, we had no particular, the idea was CVKs, okay. And then after that, we just put names, I think maybe in alphabetical order. But I think the idea was CVK, so we put his name first anyway. So, yeah. So we looked at this, and you can see, of course, there is the lifetime of this state was also not measured. So there is an incidental thing. We could put the thing vertical, so that the slit is vertical. It only, with using the lens, it only looks at a small part of that beam, and then you can make it travel. There is a way you can move that downstream, and then you can actually measure the lifetime, because the time is translated into distance, and that is what is done here. And you can actually measure the lifetime. So this lifetime was probably measured for the first time. In any case, this is the spectrum. This is a very weak transition here, shown by the red, 3489 angstroms. And so you can see that by applying a field in one direction and reversing it, there is a shift in the opposite direction. Okay, so you scan in terms of height, and that shifts in the right direction. And the neutral lithium excitation, there are other lines which are coming from lithium, known lithium lines, and they don't shift, okay, whichever way the field is. So this is very clear, and somehow I find that this kind of thing has not been used elsewhere. I don't know for what reason. Maybe because we published in Ramanna, and in those days, CVK was very strong about this, that we should support our own journals. I mean, if we don't support it, who else is going to? So it was always Pramana, and maybe once in a way other journals. Nature, of course, I said that was an exception, because Probir insisted that you should send it to Nature. But Bhattacharya was very conservative, but no, you have to do. So anyway, we sent it, and it came back without any, comments, critical comments. So but as I said, Pramana was one of the journals that we always sent it to. Okay, so then, I mean, inspired by this, I thought that maybe there is an excited state in hydrogen. It's just a 3-body system, 2 electrons and 1 proton. And there is a excited state which is due to the 2p2 configuration, triplet p even, and that is at an excitation of about, an excitation of 10 electron volts or so, but the binding energy is very tiny, 9.5 milli electron volts. And it decays by three-body decay. It decays into a neutral hydrogen atom, an electron, the other second electron gets ejected, and a photon. And that photon energy is slightly less than the Lyman alpha. The wavelength is slightly longer, but it's a continuous thing because it's a three-body decay. But the lifetime is almost unchanged, like 1.6 nanosecond, as is for the 2p state in hydrogen atom. So we said we'll look for it. So before the pelletron was to come on, we searched for it here with the ion source of the cascade generator. I built, probably this was the first time I built some apparatus from scratch, including an electrostatic analyzer and so on. But we didn't find evidence for it. We tried to improve the efficiency of the photon detection by evaporating cesium iodide and so on. Anyway, we couldn't find a positive signal, but we could put a approximate bound of being less than 10 to the minus 4 of delta electrons. Then we thought we'll do a better experiment much later when there is a student from CBS who wanted to do a project. And they come for about 6 months or so. So we built we designed an apparatus. He learned CAD/CAM for the first time. We got it fabricated in the workshop, and we had all the necessary ingredients to do this experiment. But somehow the accelerator failed us. This was an ion source in Van de Graaff, which we were asked to use, but somehow it never gave the beam when we needed it. And so anyway, finally it had to be dismantled. But all these ingredients are still there. And I think this is an interesting problem, especially because such a different way of looking at it was proposed in Fermilab. Namely, if this excited state exists at this kind of energy, then you can populate it by having H minus and having a 2-photon absorption. So they had proposed it with their LINAC, which makes the proton beam relativistic before it gets injected in the synchrotron and so on. And if it is in opposite directions, then it gets Doppler shifted the right way. So you can have 2-photon absorption with lasers of normal wavelength, visible light, those kind of wavelengths. But somehow that experiment never got done. I don't know what the reason was, but it seemed to be a beautiful proposal. But somehow, so this is, I think, in my view, an open problem still. Okay, then experiments with the pelletron. So these are some of the apparatus. You might have seen this over the course of the last 2 days. This is the high energy gamma ray setup, barium fluoride array, which was basically Deepak Chakravarti's idea. Then we had this 38 BGO setup where you can get a multiplicity of the gamma rays, a better handle on that. With heavy ion reactions, you populate rather high angular momentum states. So you require a large number of such detectors if you don't want to sum up the gamma ray transitions, low-lying transitions in one detector. So anyway, then we built a small, of course, the detectors were bought. Then we built this neutron time of flight array because we wanted to do these nuclear level density experiments. And we started out using making measurements using protons and alpha particles. But then, of course, if you want to deal with heavier nuclei, then they emit neutrons from if the compound nucleus de-excites. So you have to build a neutron array. So this is a 1 meter by 1 meter array. So I've just shown 2 pictures there because this is how it looks when we had assembled it. And then we had put a lead shield to stop the low energy photons. And it looks a nice picture. That's why I just put it in here. And then we are also involved in one experiment of the first implementation of the INGA collaboration, which has been a very successful collaboration. Obviously it has entered now the 18th year or something like that. This has been going around in all the 3 accelerator labs and I think involving many good experiments as well. So in the first implementation of INGA, I think there were something like 8 detectors, if I'm not mistaken. And this was the only non-gamma ray spectroscopy experiment. We used the gamma ray detectors with fairly good efficiency just to tag on to the compound nuclear decay and the final state in palladium. Okay, some interesting physics results on the giant dipole resonance built on high excitation energy states and also high angular momentum states in nuclei. Then the excitation energy dependence of nuclear level density, melting of shell effect in doubly closed lead region, and the radiative transition in 8 beryllium, which is itself an unstable nucleus in the ground state. So these are just some pictures to sort of orient things. This is giant dipole resonance. Basically, this is a cartoon, of course, the protons oscillating against neutrons. Then the level density, this is a picture from a paper of Niels Bohr in Science in 1937, where he shows nucleus at low excitation has few levels spread far apart, and then as you go up and up, the density increases, and then he shows a lens on that, and then there are overlapping levels. So that's the idea, that the level density increases rapidly as the excitation energy increases. Then I will say something about a peculiar observation in the course of measuring protons and alphas in excited nuclei, evaporation kind of spectra, which may indicate the existence of the pairing reentrance effect in nuclei. We know that the pairing correlations decrease as you excite the nucleus, as the temperature rises, but also they decrease with angular momentum. But if you are at a finite angular momentum and now you raise the temperature, you can have a situation where reduced pairing correlation, then they can develop as new states become available, single particle states become available, and then again they disappear. So this is the reentrance phenomena. This has been widely studied in condensed matter systems in superconductivity, where you switch when you have a magnetic field as well, and there's an interplay of temperature and magnetic field. Okay, so then this is a prediction of Ramurthy, Kataria, and Kapoor about the effect of shell closure on the nuclear level density. And this is something that was, this is a 1970 paper. I think it was not tested till we did this experiment in about 40 years later. And then the prediction of a radiative transition in beryllium-8 by Langanke and Rolfs in 86. And again, the first experiment was done by us in 2005 or so, 2005, and then we repeated it to get a better precision later on. So I'll quickly come to that. I'm probably going a little slow. So is it not moving? Oops. Somebody has to help me. Or I can move here. Oops. Oh, it has skipped one. Okay. Okay. Yeah. So again, this is a very busy slide, but this is just to give you an idea that by measuring these gamma rays and by extracting this by strength function plus compound nuclear decay where you don't have an enhancement due to the giant dipole, you can extract these strength functions and relate them to the photoabsorption cross-section of the ground state. And they quite often are very different. And so our first experiments were done in the so-called inclusive way, where you just measure the gamma rays. So you only have to distinguish between neutrons and gamma rays. And so this gives a certain kind of strength function. But then sitting at one energy, using the fold detectors that we had, of course, that was 38. In the beginning, we used 14 VGO detectors to get kind of feeling for what is the angular momentum that is involved. And you can see that the shape subtly changes as you go to higher and higher fold. So in order to explain this, you need shape fluctuations in the excited nucleus and also some triaxiality. So normally in the ground state nuclei are either spherical or prolate deformed or oblate deformed, but there are some few cases of triaxiality as well, and we need these shape fluctuations and also some triaxiality. So this is the basic idea of measuring these giant dipole resonances. Okay. We did also exclusive measurements addressing the question of Jacobi transition. What is the Jacobi transition? In the liquid drop regime, and indeed in gravitating systems, as you spin an object faster and faster, typically at low angular momentum, it becomes oblate. It becomes like an idli. And then you spin it faster and faster, it becomes triaxial, and then ultimately becomes prolate. And that's the so-called Jacobi transition. It becomes prolate. And the J critical, where this happens, is fairly high in heavy nuclei. It's like J equal to 80 or something. So it would be rather difficult to see in heavy nuclei. But in lighter nuclei, this moves to about 20 to 30. And so we thought that might be a better bet to try to look at such thing. And we were, of course, guided also by an experiment that was done in VCC, which claimed to have seen the Jacobi transition in an adjoining nucleus. Of course, there's an inclusive experiment. So we thought we should do something better to see if the effect that they are seeing is due to an unknown background. I mean, reaction background. And so we measured this in coincidence with a reaction product detector, which is the so-called parallel plate avalanche counter. So we put this at forward angle. So this detector sees a very high count rate of up to 1 megahertz. Okay, but the PPAC is good for that. I mean, so this was actually made by Suresh Kumar. I don't know if he's here, but in any case, so this handled that very high count rate, at the same time told us through time of flight that this actually was a reaction that we are looking at from the compound nucleus, not from some transfer reaction and so on, or a quasi-elastic reaction. So we did this at 2 energies, and the results are here. You see, of course, the gamma ray spectra, and you also see that when you do the gating using PPAC, you find that this contribution is actually coming from a non-compound process. So this was a background, and you can see this factor. I mean, this is like a factor of 5 or so. Okay, so this is not an insignificant background and lower. And when you fit these spectra using a statistical code, there are so many other uncertainties that this adds up, and you can get sort of different results. Of course, if the effect is marked, then you won't miss it. But we thought that this should do better. So in fact, at the higher energy and the higher multiplicity of gamma rays, we did this in coincidence, of course, with the multiplicity, the barium fluoride, multiplicity counters, and then this PPAC. So we could see that for the higher fold, you see a very narrow peak in the strength function of the. So you can convert this into a absorption cross section. I mean, the reverse thing. What you see in this process is the decay from excited states. You can convert this to absorption cross section using detailed balance. And you can see that the higher angular momentum of this. So we confirmed that there is a Jacobi transition in this nucleus, but with more confidence, because now we have done this in coincidence with the fragments. So in coincidence with the products from a compound nuclear reaction. Okay. This experiment, I think I will skip. This is a very nice case, again, thought up by Deepak Chakravarti, that you can actually probe the giant dipole resonance built on a very specific state in carbon-12. And this is a very interesting state. The 15.1 MeV state is about 8 MeV above the threshold for alpha emission, but it's still very sharp. Why is it sharp? Because there is a selection rule that prohibits its decay into alpha. It's a T equal to 1 state, so obviously it can't decay into alpha plus beryllium-8 ground state, because that's T equal to 0 in the final state. It is also prohibited from that. So that's how it lives very long. And therefore, you can look for, you can populate this nucleus by 11 boron plus proton, and then look for the de-excitation in coincidence with this 15.1 MeV gamma ray. So you have to have at least 2 detectors to do that. And then you look for the giant dipole resonance built on this 15.1 MeV state. And this shows a very different character from the ground state GDR. So you can see here that this is what you expect from the giant dipole on the carbon-12 ground state strength function, and this is very different. Unfortunately, again, we have the number of theoreticians, certainly at that time in 2008, was so few that we could only say that there is a big difference, but you can't compute that. There's no theoretician who can compute that. We did talk to whoever were nearing retirement and so on, but somehow it didn't happen. But this is an interesting case because this is a very unique state, and I mean, this is a very specific sort of measurement that we did. Okay. Nuclear. Pardon? So no, you can see that the data points are the same. So you can fit this using some ad hoc strength function. Okay, this is not a theoretical calculation. We just say that if the strength function were this, then it would fit the data using the so-called radiative capture plus including the so-called direct semi-direct effect, where in the intermediate state you excite a giant dipole. So, but it's an ad hoc thing. So we don't have a basis for why we use that particular strength function. So that has to come from theory. And unfortunately, there is no theory. And it should have actually come from theoretical groups in India, but somehow, okay, that is a dying breed. At one time, I think in the 60s, 70s, there were lots of nuclear theorists, and that decayed. Now, of course, there is a new breed, which is now a new set of people which is coming up in. But of course, there are other interests also that they have. In Roorkee, for IIT Roorkee has a pretty strong group of nuclear theorists. So hopefully, things will change. That's good for when you have all these nuclear facilities around, right? All these 3 accelerator facilities. Okay, so let me go quickly to the next set of things, which is on nuclear level densities. Now, nuclear level density is a very fundamental quantity associated with the many-body fermionic system, which is the nucleus. And indeed, the first calculation for nuclear level density is the number of levels per unit energy in the nucleus as you go up in excitation energy and angular momentum. In principle, there are other quantum numbers like the parity, isospin, and so on. And this was calculated for the first time by Hans Bethe and he used in that paper the Ramanujan-Hardy partition formula, the number theoretic formula, quite interesting. And okay, so that has to do with theory, but how do you measure this nuclear level density? The only direct way of measuring this is through counting resonances, but that's in a very narrow range of energies of the neutron. The thermal neutron energies, you can actually get resonances. If you go to higher energies, these things start overlapping. You can't count the resonances. At lower energies, I mean, the neutron threshold is something, so you can't go down. So this is done in a very narrow energy region, also in a very narrow region of angular momentum, because you can only, using thermal neutrons, get to S or P wave scattering or reactions. So from that, then you extrapolate using some theory. So the other information that you can get is by looking at heavy ion fusion reactions and by looking for the highest energy particles that are emitted from a compound nucleus. Of course, you don't get an absolute number from that. You can scale it up in all the nuclei that you are dealing with, and you will still get the same answer for the spectrum. But at least it gives you a feel for what is the excitation energy dependence. And of course, if you put multiplicity, throw in the multiplicity using these multiplicity detectors, then you can get a J dependence as well. So this was an idea of Deepak Chakravarti when he was working in Stony Brook, and we carried this out in several systems, mostly in the A equal to 100 region. And so lots of papers and lots of theses also, at least 2 to 3 theses were on this. And the idea is that the excitation energy dependence of level density goes at exponential of square root of the effective excitation energy, where you subtract the pairing part and the angular momentum part. And it can be parameterized in terms of AU equal to a liquid drop contribution to ALD, and then a shell correction. Which was first devised by Strutinsky and which was used by Ramurthy, I mean, who proposed that such a thing should happen. And they didn't cast it in this form, so it is still known as the Ignatiuk formula. And Kapoor regrets that we should have just written this formula in our PRL, and it would have been called the Ramurthy Kataria Kapoor formula. But anyway, so basically there is a shell effect. So if this delta S is large and positive, and it's as much as 13 MeV, so at low excitation energy, this can make a significant impact on the level density parameter. It can significantly lower it. And then there is a damping of this through the gamma parameter. So we thought we could address this excitation energy dependence, and that's what we did in the case of, okay. So this shows, again, don't be scared by this slide. This is just to show that there are many things that we did using initially the particle detectors, which have sodium iodide, which allow you to discriminate between protons, neutrons, alphas, and gamma rays. And this was the rough setup, multiplicity counters and proton counters. And we measured single spectra, then did this in coincidence with BGO multiplicity. And what we found is that a very unassuming type of continuum spectrum, which you observe in singles in the inclusive spectrum, suddenly acquires structure when you gate it with the multiplicity. And it almost looks like a giant dipole resonance that you saw in earlier spectra. And we have a kind of rough idea what this might be arising from, as I said, from pairing reentrance. But initial calculations do support that, but we don't have a really good calculation to compare this with. So we did this in various systems. We also showed that this is not background. We did this, as I said, in coincidence with the INGA array, but we also did a forward-backward symmetry. We have compound nucleus decays, there should be forward-backward symmetry. And we showed that in this measurement here, where you see symmetry to within the errors of the measurement. And so this bump is an enigma. So as I said, it could be due to the pairing reentrance effect. In fact, there are some shell model Monte Carlo calculations, which in some other nuclei, nobody has performed a calculation except for this in some other phenomenological way by a Ricken group, and that more or less agrees with the data, but not in its entirety. So this could be an explanation of that. And okay, so then the melting of shell effects. So this is, as I said, an experiment inspired by the Ramurthy paper. And we carried this out using a very to my mind, poor man's way of a radioactive beam, in that we used transfer fusion reaction. So you take a lithium beam, transfer a triton, and then you detect the alpha particle. So the alpha particle tells you what excitation energy you have populated in the nucleus. And as I say, poor man's, because we don't have a triton beam, and you need neutron-rich both targets and projectile for doing this experiment. We don't have that. We don't have a triton beam. So anyway, this is a poor man's way of doing it. And so we did this for two targets, one for lithium-6 alpha T on thallium-205 enriched isotope, and then one on tantalum. And we see the effect of this delta on the big shell correction as a function of, and then there is excitation dependence, which we used to put a two-dimensional bound. So the parameter space of gamma and the delta A, which is typically 8 for nuclei in the liquid drop regime, that we bound to this. So it has to lie somewhere in this area. I thought this is a nice way of representing this, and this is the paper that was written on that. Then the rotating dumbbell. So we measured this, as I said, radiative transition from 4 to 2. Here, yeah, 4 to 2. And using, of course, we did this in 2 steps. In the first case, we had poor, precision, almost a number with 30 plus minus 30 error bar, 30% error bar. Then we improved on the experiment because the main background was coming from the Kapton foils, which isolated the helium gas at about 0.7 bar from the vacuum, which is of the order of 10 to the minus 6 millibar in the exit and the entry side from the accelerator and from the exit towards the Faraday cup. This is also, by the way, the first time a gas target was used in pelletron. I don't think anybody else has used a gas target, apart from, of course, some jet, which you might have used, but really thick gas target, about a foot long and 0.7 bar pressure. I think this is the first time this was used. Sorry, overshot. So anyway, so the idea was that you look for the photon in coincidence with the 2 alphas. So you do a complete experiment, alpha, alpha, gamma, nothing more than that. The background comes from carbon 12 excited state, and that is taken care of by this heavy met shield around the entry and exit foils of Kapton. Kapton is a material which withstands radiation. So we didn't have to change the foil throughout the run of about 10 days or so. Okay, it withstands radiation damage resistant. If you put a mylar foil, it would die within half a day or 1 day, but Kapton survives. So, but then it gives rise to a background which is taken care of by this. So the background from here doesn't reach the BGOs. And so this is a relatively clean experiment. The uncleanliness came about because there's some shortcut that we tried to do, and then that led to a small, tiny air leak. And so the nitrogen contamination gave rise to some of these background counts that you see. But nevertheless, it was much better than the earlier experiment and good enough to get a paper in PRL. And so this doesn't agree with ab initio calculations of Viringa. They agree with the alpha cluster model calculation, which is not really the right thing. But we think that, and Viringa also thinks that this disagreement is actually telling you that it's not only the once you form the resonance that guy decays, but even before forming and after it decays, there can be radiative processes that can contribute. And so these amplitudes all have to add it up. And so he said, he promised that I will do this calculation sometime. That sometime has not yet happened, but he's sure that this must be the cause of this discrepancy. So it's good. I mean, I hope someday somebody will be provoked to do this calculation better, including the whole reaction mechanism. Normally, the structure fellows stay away from reaction. Okay, there are 2 groups. So this combines them. Okay, now what is the future for such an experiment? Is I think if you have a gas jet target, then you could do a much cleaner experiment, because then you have only that gas jet, which is about 2 millimeter by 2 millimeter, and vacuum elsewhere. So there's no question of background from the foils and this and that. And also you can get pretty thick targets, by the way. You can increase the count rate, the event rate, by actually increasing the beam strength. And this should allow a measurement of the 2 plus to 0 plus transition, which should be another factor of 20 or so smaller than what we have measured. We measured a branching of about few times 10 to the minus 7. And so 10 to the minus 9 is what is the sensitivity needed to make such a measurement. And in principle, this is possible. But another interesting thing that could be done is you look for the transition in the resonance itself. So if you populate the beryllium-8 on the higher side of the resonance, say halfway or something like that, then you can look for its decay halfway down on the other side of the resonance. And that should tell you about the E2 matrix element connecting the same state, in principle, quote unquote, the same state. So it will tell you about the E2 moment of this resonance, which lives how long? It lives only for 10 to the minus 23 seconds, right? So you have made a quadrupole moment measurement on that time scale. Should be quite unique, I think. So these are the two things that could be done, and that will be for the future. Okay. We also made another measurement some time around maybe 15, 20 years ago in IUAC, where they developed the first radioactive ion beams for nuclear physics experiments. Of course, there is a radioactive ion beam program at VCC, but they haven't got to the point where you can do a reaction with those radioactive ions. Very low energy, you can implant it, you can look at the radioactivity and things, stuff like that. But this gentleman called J.J. Das, he had this idea of slightly tinkering with the optics of the recoil mass separator which they had built at IUSC, and to get a beam of beryllium-7 with greater than 99.9% purity. Most of the radioactive ion beams that were there at that time and even to this day are a sort of cocktail of many radioactive ion beam species. Then you have a magnet which separates them out. Sometimes you don't even separate them out completely because there's ambiguity in Z by A and things like that. So anyway, so this was a very nice beam, and with just 3,000 particles per second, we could carry out this transfer experiment. This is the so-called ANC method of basically a direct reaction method. This is the reaction, beryllium-7 beam, very pure, but very small strength, and almost like a Van de Graaff beam, or almost like a tandem beam, and shoot it on a foil of polyethylene, which has deuterated polyethylene, okay, so which has deuterium in it. And then you look at this boron. So we don't look at the neutron. It's a two-body decay, so it's enough to look at the boron. And neutrons are always harder to look at. And at a very low beam energy, whatever is provided by the accelerator, with lithium beam, there is a certain energy that you can do. And this was also, there's some novelty in the way it was produced. You had to make a rotating polypropylene film, which JJ did right before, and then so that it doesn't get burnt out. We didn't use Kapton. And finally, anyway, we made this measurement, and so the results of this measurement are here. So in addition, of course, we did the elastic scattering. So in order to analyze this data, you need the wave function of the proton at large distances, the so-called ANC measurement. So you measure the transfer cross-section as a function of angle, then you interpret it in terms of some direct model, direct reaction model. But you need optical potentials there in the incoming and outgoing channels, and also the bound state of proton in boron 8. So there are three potentials that come in. So there are many of these potentials in the market. So we did something like 5 into 4 into 4, and to estimate what is the systematic error coming from such an analysis. You make a histogram plot. You extract each time S17, which is that the cross related to the cross section at very low energies is parameterized. You remove the exponential factor, otherwise the cross section drops as you go down in energy, and this can be parameterized in terms of the S17. And so there was this Chinese experiment which claimed that there's a big discrepancy between such a measurement and the direct measurement, where you measure the gamma rays using a radioactive target. And we showed that no, at the 10% level, we agree with this thing. So I think it helped settle the question. But more importantly, since the cross-section is now of the order of tens of millibarns per steradian, you can use this in other radioactive species. So typically, radiative capture cross-sections are of the order of picobarns or tens of picobarns, whereas this is of the order of tens of millibarns, much easier to do. And so you can get a quick and rough estimate of the S factors relevant to that reaction at the level of 10%. If you want to go to more accuracy, of course, you have to do the radiative capture experiment. And also you have to do, in many cases, underground or the recoil mass separator and all that. So, okay. So this is one thing that I would, then I come to the underground lab. So I have been involved in the INO project since about 2002, when CVK told me to get into this business. And because it requires more experimentalists, so nuclear physics, he said, you have the training to do that. And so we went into this. The idea was to build a large iron calorimetric detector, 50 kilotons, and to measure atmospheric neutrinos. And one of the key problems that we were hoping to solve was the so-called mass hierarchy problem of neutrinos. So, of course, before you get there, you have to build smaller things in order to make sure that you can indeed hope to build that. And so the first thing was to build a magnet. And so we built this magnet. So you see Bhatia here, Suresh Kumar, and I think I took the photograph, so I'm not in the picture. And we built this 35-ton prototype. There's a lot of learning that went into this because it's not easy to build good magnets. And this is a very different kind of magnet. It's not a magnetic dipole where you have two pole pieces and you have a magnetic field in the middle. The magnetic field is internal to the iron. And there are these two sets of coils here, you see. So they set up a magnetic field in this direction and the other direction, and it's internal. So we goofed up on the the estimate of the magnetic field, and we had provision to put another set of coils. So we had to actually double the number of ampere turns. We knew that we could go wrong, and so we had provision for that. But this is what happens. I mean, you build your first magnet and there are effects which you don't anticipate. And it turned out that the way we were cutting these plates was using arc cutters. And that spoiled the surface of the magnet, or the surface that was being cut. And that contributed to a huge amount of magnetic impedance. And so we got only half the field that we had expected at that. So anyway, so we learned this, and then the next time around we improved on that. And it did a much better job, simulation to measurement. So the 85-ton mini ICAL detector at Madurai was built in 2018, and you see muon tracks of either charge, mu plus and mu minus, bending the opposite direction. And in fact, I think, I don't know how many, but maybe about 3 theses or 4 theses came out of such work. One of my students also worked on this to try to see if you can measure the internal magnetic field. It didn't work out, but in any case, many things that were attempted at this. And the good thing was, of course, that the simulation reasonably agreed with the measurements, which were done by Hani, one of the other PhD students or INO students. Then we had hoped to build a 800-ton engineering ICAL. It was hoped that this will be built in VCC, but this has also not happened for various reasons. And of course, now that the INO project is more or less closed down, we have to look for another underground site to do things which may not necessarily be driven by ICAL, but by something else. So anyway, in the course of doing this, lots of things were developed, and I hope this thing doesn't just evaporate. All this know-how, where we built glass RPCs, we had industry coming in with automated ways of putting in the buttons between two large glass plates of 2 meter by 2 meter, very thin glass plates, so they had to be handled carefully. There had to be the spacers had to be put very precisely. The gas system, closed loop gas system was evolved. There were chips that were designed and fabricated and used. Then there is a high voltage, this is a HP TDC. So the TDC card and the high voltage card that was made plus minus 5 kV to supply voltage. So you just send in plus minus 12 volt and you can get a high voltage on the. So many things were developed. A front end board for each of the, the 128 channels in the RPC and the triggering system. All these things were developed by people here and by people in BRC. So if you had built the engineering module, all that would have been immediately used. I'm still hoping that that will be built somewhere, maybe nicer, because the VCC backed out at some stage. And so there are lots of students involved, by the way. Lots of student outreach was done, and these are some pictures of that. One of the PhD students, Nitali, she worked on searching for exotic particles, dark matter. One time, the KGF events, which are anomalous, and if they are real, then of course they can be looked at much more sensitively with a large detector like ICAL. And so we had made some simulations of that, and we showed that this indeed, in a year, you would actually be able to say whether these are real or not. Similarly, this such a large detector can also be used to put upper bounds on possible magnetic monopole fluxes, the upper bounds that we could get in about 5 years for such a thing. Of course, in addition, building a plastic scintillator on the walls, that is about 5 times better than the best experiments at that time, macro, which is a big experiment, I think 30 kilotons of plastic or something like that in Gran Sasso. So this formed part of the thesis of one of the students. Then the other student, as I said, Neha, she worked on this idea that, we are getting stuck with the site in Theni. And so Murthy asked this question that, can this not be done at a much shallower depth? And we address this question. It can be, provided you have a veto counter with 99.99% efficiency for muons. Because at 100 meters, you go down in the cosmic muon flux from the surface by only a factor of 100. If you want to go to the level of 10 to the 6 down, then you require a veto counter with 99.99% efficiency. So we said, okay, let's take a look at it. Can it be done? I was a bit skeptical at that point, but I said, let us try it. Let's do the experiment. And we, whatever, beg, borrow, steal in TIFR, whatever things are lying in the cupboards, unused and all that, we put that together. And we also involved, by the way, the INO graduate, the GTP program students in that. They were quite excited. I told them that, no, this might even make a paper. I'm not guaranteeing that, but it might make a paper. So they worked very enthusiastically on that. In fact, that formed part of the thesis of Neha. And to my surprise, we got a veto efficiency of 99.98%. Now that was quite remarkable, because then I said that, okay, is there such a thing elsewhere in the world? And the first thing, when you type in this thing in Google, you find that there is an experiment mu2e in Fermilab, which is building, they say, the size of a house, a large American house. The hut of plastic scintillator. Wow. So we contacted the Fermilab guys and they said, yeah, we are building that. We said, can you help us, get some scintillator from you? Because they're manufacturing their own scintillator. After one or two rounds, the director of Fermilab he made just a casual remark. Yeah, we can do that. I didn't believe it. So we wrote to them an email saying that, is this really what you said? He said, yeah, this is what he said. So it is about 40, 50 lakh worth of plastic scintillator. So some students and some engineers went from there, and they saw what was going on. They learned a few things from there and so on. And we got the plastic scintillator for basically free, only the transportation and the cost of, students going there and staying there. And of course, the other things we had to do. So we bought the Kurare wavelength shifting fibers that we had to put in there, the silicon photomultipliers, which also they helped us. They talked to Hamamatsu. They're not willing to give this Hamamatsu to silicon PMs, but they agreed to do that. And the same design that they were using there. So we got all that. So now these things are fabricated. They look very impressive. The panels of this. Unfortunately, now the lab in Madurai has to close down. So we can't get this. And also there is a lacuna in the sense that the electronics for that went through many things, and we thought we would get some chips from CERN, Brookhaven, this, that, but finally we had to do something else, completely different, and that is taking time. So it would have taken about maybe 1.5 to 2 years to build that, and that much cannot be supported with the INO project basically closing down. So we have to find use for that. Certainly in experiments which require veto counters, maybe overkill for some of those, but we could perhaps use these things, or we have to think of some way of using these, because these are very professionally made by the INO group, beautiful panels of plastic scintillator. It is also again part of the thesis of Mamta Jangda, who went to Fermilab that time. We simulated this also, because one of the doubts expressed by Navamandal is, okay, you can have a 99.9, but what about the secondary reactions of the muons in the rock? They will, give a lot of background. So we did that, and that was again part of Neha's thesis, and we showed that the false positives are much smaller than the event rates that you get. So we think that these results are quite promising. So in principle, you could do it at a shallower depth. Of course, not that you would do this. You would do this only if pushed to the wall. So if you have a deep side, of course, it is better to go to a deep side. But nevertheless, this has the advantage, by the way, that you have many more muons. So your counter is all the time, or your detector is all the time being tested. If you are in a place where there is no background, you start wondering whether the counter is really working or not. It's just no count. So maybe things are not working as they should. Whereas here you have them all the time coming. So you can you can count these things and so on. Anyway, so that makes a case for a possible shallow thing. Then also we have in recent times, due to the enthusiastic support and ideas and so on of Basudev, we have been working on this deuterated liquid scintillator. This would, if it really happens, it would be the next generation from the snow detector, which basically solved the solar neutrino problem. Okay, that is a beautiful idea of Chen in '84, where he said that you use deuterium, heavy water, to look at both the charge current signal as well as the neutral current signal. So what you see missing in the charge current signal, you recover completely in the neutral current signal. The neutral current is oblivious to the type of neutrino that is interacting with the medium. And so they basically solved that problem. And indeed, McDonald, so unfortunately, Chen didn't live long. He passed away, I think, in the 90s. So, of course, dead people don't get Nobel Prizes. He was actually heading that collaboration. And so, but McDonald did a fantastic job, led the team that solved this problem. And he got the Nobel. He shared the Nobel Prize with Kajita, who did experiments with the atmospheric neutrino detectors of the Super Kamiokande. So anyway, the idea is, again, there's a lot of things that have been written here. So anyway, the idea was that India is the largest producer of heavy water in the world. So we have a natural advantage if the Heavy Water Board agrees to do this. So we contacted them. They said, yeah, should not be a problem. Oh, how much worth this is? Oh, this is like 7 reactors worth of it. Yeah, should be possible. The then heavy water, what is the chief engineer, he said that. And so immediately 2 committees were formed, one by the director BRC, who formed a committee to look into, doing the R&D, developing this scintillator, and the other one to look at the science possibilities. I think Ramki was the director at that time. So he formed this committee, and then they have been meeting not in the recent past, but right now we are working on something else, a DLS for solar neutrinos. So maybe once that happens, we'll again meet and discuss this. But the idea is that if you have a deuterated liquid scintillator, you can do the next generation of experiments, the more precision type of experiments. And what can it do? Of course, it can measure supernova neutrinos, which this paper is about. Okay, but nobody would give you so much of money just to build a supernova neutrino detector. But it can certainly do solar neutrino physics with a higher precision. And so you can measure this. You can look at the survival probability of the electron type of neutrino, which should have this kind of dependence. Sorry, here PEE, that the probability the electron type of neutrino survives from about 0.57 or so, it goes down to about 0.3 or so. This is according to the so-called Mikhail Smirnov-Wolfenstein paradigm and large mixing angle. And there is very little data in this region where the so-called non-standard interactions show a very different behavior, at least some non-standard interactions. So you can probe this, so you can address this paradigm in a much more precise way. And there is also the so-called day-night effect. That means you should observe a difference between the day and night because of matter effects of the Earth's, mainly the core, but also a little bit due to the mantle. And so this is a very preliminary calculations. This could change a little bit, but the idea is that this day-night effect could be measured more precisely with a DLS detector. Why? Because the deuterium has this has a neutron and a proton, and the nu E interacts with the neutron. You don't have a stable neutron target, right? So the next best thing is a deuteron. And the charge current interactions typically have cross sections which are much larger than the elastic scattering on nu E. And so this is a very good way of, so the things that have been measured using the elastic scattering on electrons, they have only measured this at the 1 sigma, 2 sigma level. So it is not even clear that there is a day-night effect from the data of Super Kamiokande 50 kiloton detector, or from SNO, which is a 1 kiloton D2O detector. So if you have a liquid scintillator, then you could do this much more precisely, and this effect could be seen. And there are other things that this could do, whatever, dark matter, non-standard interactions as well. So the possible plan for such a eventual 1 kiloton deuterated liquid scintillator with maybe 95% of it deuterated is that you start off with pure D2O like SNO, but with much higher quantum, double the quantum efficiency photomultiplier. They are now available. They didn't have them at that time. So already you reduce the threshold from 5 MeV at SNO to 2.5 MeV, and this will address this part of this region. Okay. The next step would be to dissolve a hydrogen-based liquid scintillator in a small percentage in heavy water. This R&D has to be done, so one can't say that this will be entirely. This is definitely possible, but there's a strong possibility that this can happen. In fact, scintillator in H2O that is being worked on by the group at Brookhaven to measure reactor antineutrinos from a ship or something, and to monitor, whatever activity is going on, let's say Iran or something, and or any other, reactor. And so whether it is possible to put a hydrogen in D2O, it looks plausible, but nobody has carried out this. So we will enter this game also. And of course, the ultimate thing is that if you can make a completely deuterated or almost completely deuterated lipid scintillator with D2H of greater than 10, then that's fantastic, because then the threshold can be of the order of 100 keV. So that would be great. Okay, so where do we do it? To do these measurements, especially on the okay, so you need a deep underground facility. Okay, so for housing experiments which target neutrinos of all kinds, atmospheric, solar, geoneutrinos. By the way, the Himalayan region, if you have a lab in the Himalayan region, the Himalayan region is a hotspot of thorium and uranium. So you should see many more geoneutrinos than were seen by, let's say, Borexino or by Super K. Then dark matter, neutrinoless double beta decay. Of course, if you have I think this such a project should ultimately be driven by the nuclear astrophysics community. That's a much bigger community, and it's basically an extension of what they do in nuclear physics. So many experimentalists, and so I think they have in principle agreed, but it has not happened yet. Ultimately, it depends. Somebody has to write a proposal for that, put it down in writing. Then there are other things that can be done, seismic measurements, radon monitoring, which can give you an inkling of an impending earthquake, let's say, by anomalous, changes in the concentration of radon that you see either up or down, depending on how this dynamics goes in the rocks surrounding. And then you can also do geomagnetic measurements. You can map this magnetic structures in rocks in 3 dimensions, and also time dependence of that. Perhaps even a gravitational wave detector can be built here, because the Japanese have already, I think, built this Kagura detector underground. That has an advantage that seismic noise is less if you go deep underground. So anyway, so this is the possible site. I mean, we don't know whether this will be cleared by the so-called NSA. But we have put it up through the chairman that there is a tunnel which is about 9 kilometers long, and about 2/3 of the way there is a peak here at 5,100 meters. So you start out with about 3,000 and odd 3,070 meters or so, and you go up to 1,500. So it's 2,000 meter plus overburden, which is about 1.5 times that which we had in Theni. So already the muon background is much less there. And of course, in the future, if there is a need for that, then there are other peaks which are higher. In fact, there is a peak which is about 6 kilometers away here, so-called Shikhar Peak, which is another 1,100 meters higher than this. So if you go there, of course, then you should make it the deepest lab in the world, okay? Because the Chinese lab is about 2,400 meters rock overburden. So we would be probably the second if we get to Atal. And these are photographs sent by Murthy on the picture of topo picture from the southern portal side, and this is from the northern portal side, where there is a much steeper slope. The advantage of this Atal tunnel is that, of course, you get a large rock overburden, but also you have minimal tunneling. The cost goes down, the time to do it goes down. So that would be absolutely the best option. But the thing is that this is also going to be used by the army when needed, and so we need NSA clearance. So we were told that let the elections get over and then we'll see. That's the status. So now I should acknowledge all the people from BRC, TFR, many friends and colleagues. Deepak Chakravarti, Suresh Kumar, Arunoday Mitra, Raut, Prakash is here, Shiva Behra, Bhatia, Badodkar. These are all engineers, Bhatia, Badodkar, Prabhakar Dalal, engineers from BRC, Vandana, Mondal, Satyanarayana, Majumdar, Bhavesh Chauhan, who was the lead author in the DLS for supernova neutrinos. Then, of course, Rajaji was a great supporter of the INO project, so lots of interactions with him. Of course, Murthy is attending this talk. Indumati, I don't know whether she's here. She has some, she may not be here right now. Amit, he was involved in the charge non-conservation experiment. JJ in the IUSC RIB experiments. Also, Sugatan was participating in the beryllium, apart from RIB experiments. And then many INO GTP students, Nitali, Neha, Petruraja, Purva, Surya, and so on. And of course, I should again end by thanking my teacher for all the things that I learned from him. Okay, so I come to the end, and yeah, a picture by my son Ved. He is also fond of photography, and so we had recently been to borrowed one of his. Yeah. So I come to the end. So I'll be happy to answer any questions.
Journey through the.
I took a
45 years.
little more time.
No, that's
but,
okay.
I
It's
hope
fascinating.
people
So
don't mind that. Yeah.
Any questions from the audience?
People may
Also,
be
the
tired
people in
looking.
Zoom line, there is already Satya has. Anybody wants to have a question there?
Somebody has a question?
No, they're just uploading.
Okay.
things.
Okay.
No, they're just
No,
uploading.
Milind. Oh,
With
Milind is
virtual
just clapping.
claps.
I thought he was raising his hand.
So, since we have already run a little faster, maybe we can start the tea session.
Yeah.
And questions can be
No
also
problem, no
personal.
problem. Anyway, this is a kind of
So-
historical talk.
Yeah.
Ran
It is a
over
fantastic
for
overview
a
of
few
things
years.
which you have done and things
And,
like that. So,
Yeah. Oh, sorry. Yeah.
In the Atal tunnel, which
Yeah.
you mentioned, for the spot, how much wide one has to go from the tunnel, one has to
Oh.
take a detour, no?
Yeah. So,
So how much?
okay.
uh.
So I'll tell you. Depends on, I mean, the engineers who actually built this tunnel, the private company which built this, they said, you tell us where you want to make a hole and we'll do it there. And so then, of course, it is within, I think, something like 100 or 200 meters. Okay. But suppose they say, no, you can't disturb something which is already there. Then on one side of the tunnel, there is very little, these pipes carrying water, gas, and so on, firefighting things and so on. So on the other side, there's nothing except for some electrical thing. They can be power lines. So they can be removed. And so you can go on the right side when you're going south to north, and then go under the tunnel itself, even below the safety tunnel. There is a tunnel and then there's a safety tunnel. You can go below that and then land up at this place. You get some additional, 30, 40 meters or something like that. But you won't disturb the left side, which is populated with something. But the engineers told us that that's not a problem. Within a day, we can make a hole and put back everything. So that's not a great issue. But some of the, of the conservative people will say, no, what if something goes back? Anyway, yeah. So we can, I'll address that at the tea time. Yeah. But all the engineers whom we talked to, 3 or 4, including our own engineers who were visiting that place from the civil engineering department, and the local engineer supervising, and then also another engineer who was involved in such tunneling projects. I mean, this can be done. No problem. No technical problem. And the issues of course, people, NGOs raising their hand and then, coming with flags and all that. That is common to any project. I mean, there's nothing to do with Atal. And in fact, Atal, they will find it a little difficult to come in that cold climate and protest. They're not like Theni, where there was an anti-neutrino march. Huh? There is not a march for anti-neutrinos, but a march against neutrinos. Yeah.
So I thanks once
Yeah.
again Datar, for a fantastic thing, sir. Thank you. I request everybody to join for the tea.
Yeah, sure. Oh, Alak has a
Professor
question.
Alak Ray has raised a hand.
Oh, please.
Sir, can you please unmute yourself
Yeah.
and ask question?
Vivek,
Yes. Go ahead.
what's the two questions? Number one, what limits you to just 1 kiloton of D2O? And number two,
1 kilogram. No, 1 kiloton. Yeah.
and number two, you said that in some of the scintillator experiments, you could go down to very low thresholds.
Yeah.
So at such low thresholds, wouldn't your geophysical neutrinos be a problem?
Okay. The geoneutrinos, right? That's what you're referring to?
Yeah.
From thorium, uranium, and their daughters and so on. They are
Yeah.
typically at a level 4 orders of magnitude lower than solar neutrinos. So we're looking at solar neutrinos, that's not a problem. If you are near a reactor, for instance, again, they are not a problem. By the way, the deuterium detector can detect both neutrinos and antineutrinos. So we are, in fact, if we can do an experiment with the prototype near a reactor, such as Kudankulam, that would be great also. We are first planning, of course, for a hydrogen-based lipid scintillator, but then you could also, once this is developed, we can put a ton of such a scintillator near there. And that, again, because the flux of antineutrinos from a reactor is much more than geoneutrinos. Geoneutrinos, by the way, are very hard to detect. But if you are at a place which is close to the thorium and uranium, then maybe we will have, I don't know what is the enhancement, maybe a factor of 10, maybe 100, I don't know. Pardon?
UV versus UV from solar versus UV from reactor.
Yeah, sure. Yeah. So the signal will also be different. If you have an antineutrino, you will get to react with the proton. Sorry, he should listen. Anyway, I have this mic is still on. Yeah. So you should actually see 2 neutrons in the final state, which is a big handle that you have. And you will get 2 ATMV signals if you put in a gadolinium or something like that. So certainly you can distinguish between antineutrinos and neutrinos. Yeah.
Yeah.
Ananda? Yeah. What's you unmute yourself?
Hello.
Yeah.
Hello, Dr. Datar. That was a nice exposition of all the things which have been done so nicely by the groups there. A quick question.
Yes.
For the magnetic, that the arc cutting doesn't, the magnetic is not as much. Is it because it becomes amorphous?
What is that? Sorry, I didn't get your question. Can you repeat it slowly?
When you do the arc cutting of the metal plate, is it because it becomes amorphous?
Yeah. So the what is that called? That is called grain structure changes such that it becomes harder to magnetize. Okay. And so the better the grain structure in terms of long grains, it is easier to magnetize. And when you do this arc cutting, you actually destroy that. And so a layer of about 1 millimeter or so goes very bad. And that 1 millimeter corresponds to a air gap of something like 1 meter. So if you have this at many places, you have maybe 6 gaps or something, then you have 6 meters additionally to whatever your loop is. And so that must have contributed to this lowering of the field that we saw. So you have to drive the fellow harder.
Right. Okay. Well, that's quite interesting to know, because many times when we are making magnets, it's useful to have that. Was something like that known, or you found that by chance?
Oh, we found that we were not getting the field in the gaps, and so we had to increase the current by a factor of 2, and that was a big learning that we got from this toy magnet that we built. But we did reasonably right, I think, for the mini iCal, because then the cutting procedure was changed by the engineers who were involved from BRC, and they did a rather careful job. And so when Honey made the measurements in the gap field, she found it agrees with simulations to level of about 5-10%, which is good. This is something that even the KEK guys told us, that in dipole magnets, they got such an agreement to a few percent, 5%. So this is good.
Yeah. Thank you.
Yeah. Thanks.
Thank you, everybody.
So with this, we conclude the Zoom session as well. And thank you everybody on to that. Thank you, Professor Datar again.